Thank you very much. Okay, thank you very much for the invitation. And I'm sorry I'm not in Princeton to give this lecture. Maybe my slides have another title, right? This is the third title, no, maybe? Okay, so I would like to discuss some relationship between hydrodynamics and Einstein's gravitation. And the Monge theory of optimal transportation will be playing a link between the two theories. Okay, so let me start. Let me mention first that there has been some works, quite recent works, linking general relativity and optimal transport. And in particular, I would like to quote the paper by Andrea Mondino and Stefan Zur, and also another work by Robert McCann. And both of them are based on the definition of the Ricci curvature by optimal transport tools in the framework defined 10 years ago by John Lott and Cédric Villani on one side and Carl Theodor Sturm on the other side. But the approach I would like to discuss today is very different and more related to the so-called hydrodynamical formulation of optimal transport. So OT for me means optimal transport. Sorry for using this acronym. And some people call that the Benamou-Brenier formula, and this goes back to a paper written 20 years ago. So the discussion I will give today is contained in the recent paper that you can find in this preprint server. Okay, so let me just briefly remind that I guess everybody knows in this room that the Euler equation goes back to 1757. And in my opinion, this is the first field theory in the history of theoretical physics. And this is also the first nonlinear multidimensional PDEs ever written. So this is quite remarkable. And so in the more or less modern notation, more like continuum mechanics notation, so you have the Euler equation here. I'm mentioning the compressible version, sorry about that, if you consider the title of the workshop. So the continuity equation, dt rho plus divergence of rho v, where rho is the density field of the fluid and v is the velocity field of the field. And we have the famous momentum equation involving the pressure, which in the paper of Euler was supposed to be depending only on the density in the compressible case. However, it is a comprehensive set of PDEs, and this defines a consistent model for fluids. And this is the compressible Euler equations in the isentropic version in modern phrasing. And again, to the best of my knowledge, this is really the first multi-D evolution PDEs ever written. So this is quite remarkable. So let me remind you just for the, as a starter, this picture of Euler and also the equation taken directly from the paper of 1757. And you can see that this is very readable. The notation are almost the same as the one we use 200 years later. So this is more like the momentum equation. And the continuity equation, l'équation de la continuité, is written here. And the density is just denoted by Q in the paper of Euler instead of rho as we do now. And there is also the incompressible version where you assume that the divergence of the velocity field is 0. But today I will only discuss the compressible case. And just for fun, let me show you the conclusion of Euler claiming, so it's written in French, sorry, but he explained that after this paper, there is no problem anymore with the principle of mechanics. because everything is contained in the equation that I have written, which is not entirely true because Euler missed the thermodynamics and there is no energy equation in these models. But he says that what is missing is uniquely analysis, which is not sufficiently developed at the moment. And it is quite amazing to see that 250 years later, the Euler equation are still one of the most challenging and outstanding nonlinear PDEs. Okay, so I guess everybody is aware of that. So let me move forward to something which is a little bit less known, that there is a least action principle behind the Euler equation. This is mentioned in the paper, but not explicitly written in modern style. So you could say the following, that these fields, rho and v, the density and the velocity fields, can be seen as critical points of an action, which is defined as an integral, a space-time integral, with respect to compactly supported perturbations, and to the condition that the continuity equation is satisfied. And the action itself is made of two pieces: the kinetic energy of the fluid, rho v squared, integrated in time, minus the potential energy of the fluid, integrated in time. And I have to tell you what is capital phi. So capital phi is a potential that can be deduced from the pressure from the following equation, that if you take the density R and you compute the second derivative of phi with respect to R, are just given by the the derivative of P with respect to the density, which is just the square of the sound speed. So the fact that the sound speed is a real number just means that phi should be a convex function. And maybe the simplest example is when P is just a linear function of the density, which is usually called the isothermal case. So when P is just proportional to R, and the constant of proportionality is, of course, the square of the speed of sound, c squared, and here the speed of sound is constant. And you can, of course, recover phi as a c squared R log R minus R. There is a minus R missing, which doesn't change anything anyway. So you can compute the potential very easily out of the pressure. And I just gave you the formula in the isothermal case, where you have the nice combination of the kinetic energy of the fluid and the Boltzmann entropy of the fluid, which is very appealing, in particular for people in optimal transportation. Okay, so now just an elementary calculation tells you that the formal optimality equation out of the least action principle are the following. So first of all, the V must be a potential vector field. So there is no vorticity in this out of this action principle. And there is Hamilton-Jacobi type equation, which is also called the Bernoulli equation, telling you that the potential theta is given by this evolution equation, dt of theta plus 1/2 of the square of the gradient of theta is balanced by the phi prime of the density. And after some short calculation, you deduce from this Bernoulli law, derivating in space and multiplying by rho and reorganizing the term, you get the Euler equation as I wrote before. And P is, of course, related to phi by the formula that I already discussed before. Okay, the fact that we are restricted to potential velocity field is not a big deal. I mean, there is some simple trick to make the action principle more precise and to include vorticity in the framework. But anyway, for my talk, the potential flows are largely sufficient. So I will not discuss more about the vorticity equation. Okay, so the least action principle is not precisely mentioned in the Euler paper, and I'm not able to tell you exactly when it was written up the way I did today, but this certainly goes back to the late 18th century or to the 19th century. Okay, and also I should emphasize that the word least action is used by tradition, but it's really a critical action principle because you see that the action is made of the difference between potential energy, which is convex with respect to rho, and a kinetic energy, which is convex in terms of rho and the momentum rho v. So you can write that as rho v squared divided by 2 rho, and this is jointly convex with respect to rho and rho v. So you have the structure of a convex quantity minus another convex quantity. So it's definitely not, it's more like a saddle point or critical action principle. Sorry. Okay, so now there is a special degenerate situation where the gas is pressureless, that is, there is no pressure, and therefore, since there is no pressure, there is no potential, and we are reduced to a more elementary situation where the action principle amounts to finding fields rho and v, which are critical for rho v squared over 2, subject to the continuity equation. And as I just said, now we have really a convex functional because there is no potential energy anymore. Of course, as I said before, it's convex in terms of, not in terms of rho and v, but in terms of rho and rho v that I will denote by m, like momentum. And this is very fortunate because the continuity equation is linear in terms of rho and the momentum m. So we have a nice structure of a convex optimization problem and linear constraint. And therefore, in that framework of pressureless gas, we can really speak of least action. And we can even try to minimize this quantity with a time boundary condition. Typically, if you assume that the time interval is 0, 1, we can prescribe the density at the initial time and the density at the final time, and we can try to minimize this quantity, and this mathematically is completely meaningful. And here you can see a big gap between the pressureless gas case and the more realistic case where the pressure is non-trivial, because with pressure, the statement that we have here doesn't make much sense. And in particular, it doesn't make much sense to prescribe the initial density and the final density. Actually, the action principle for the genuine Euler equation for a non-trivial pressure field is really related to the initial value problem, where you assume that the density and the momentum are prescribed at the initial time, and you try to see the evolution of the fluid. So it's a Cauchy problem, an initial value problem, and not a 2-point boundary value problem in time. So the fact that here I'm discussing this funny time boundary value problem is really linked to the fact that I'm discussing a pressureless gas. And why I am talking about pressureless gas? Because this is precisely the framework of the initial value of the optimal transport problem of Gaspard-Monge, which was defined by Gaspard-Monge in 1780. So this is like 20 years after the work of Euler. And this is not related to fluid mechanics in the paper of Monge, but more to civil engineering. And this is called the problem des déblais et des remblais. So how you can move some earth from one location to another one and to try to minimize the transportation cost. And so, of course, the the field has become very famous, in particular with the field medals of Cédric Villani and Alessio Figali. And an interesting feature of so this is a picture of Gaspard Monge. And the usual definition, based on the direct work of Monge, is not as I said so far. So let me just, this is a very, very short review of optimal transport. So in modern vocabulary, it amounts to find a kind of distance between two density fields, non-negative density fields, so rho 0 x dx and rho 1 y dy, defined on RD, on the Euclidean space. And what you are doing, you are trying to write rho 1 as the push forward of rho 0 by a Borel map T, or an image measure of rho 0 by T. And well, of course, in general, rho 0 being different from rho 1, you don't expect T to be the identity map. And therefore, you define the distance between rho 0 and rho 1 in terms of the L2 distance between the map and the identity map weighted by rho 0. And this is the definition of the Monge distance between rho 0 and rho 1. I should say that this is the quadratic Monge distance, because in the original paper of Monge, everything is related to the L1 case. That is, you substitute for 2, 1. And this defines the Monge-Kantorovich distance between rho 0 and rho 1. But as I guess most of you know, the most popular and useful case is the quadratic case, in which case you get this formula. And precisely in this quadratic case, we can establish the connection with the Euler model in the sense that this quantity is precisely the one I discussed in the previous slides. That is, it corresponds to the infimum of the time integral of the kinetic energy of a fluid with density rho, velocity v, subject to the continuity equation, dt rho plus divergence of rho v 0, with prescribed values of the density at time 0 and at the final time 1. So this equivalence is not a big deal, but well, this was done in this paper by Benamou and myself, 2000, for numerical purpose, but it turns out to be extremely useful, and this has been used a lot in the last 20 years. So this formula is also very useful when you want to do some generalization of optimal transport theory. For instance, if you deal with discrete structure like graphs. So I am thinking of some work by Erba and Maas, for instance, or even in the quantum case. And I'm also mentioning the work of Eric Carlen and Yann Maas, for instance. And there are many, many other possibilities. And before concluding this short section of optimal transportation, let me tell you that you can write down the formal optimality equation. And again, you get that V, the optimal velocity field, is a potential velocity. So there is a potential phi. And you get for this potential phi, the Hamilton-Jacobi equation without any pressure term. And when you compute the equation for V, you get this kind of multidimensional version of Burger's equation. So dTV plus the gradient of V squared over 2 is 0, which would collapse to the inviscid Burger's equation if I would be in one space dimension. Okay, and I mentioned this optimal equation because this will be useful for my talk in order to design a toy model for some proofs. Okay, so now I just launch without justification at the moment generalization of optimal transport in the direction of what some people call the matrix valued optimal transport. That is to say, instead of considering density fields that are real valued and even non-negative real valued function, here I am considering as a substitute for the density field, matrix valued field, capital C, which is made of 4 by 4 real matrix valued field. You will see in a moment why I'm talking about 4, the number 4. So these are square real matrix valued field C, and the field V is also a 4 by 4 real matrix valued field, and it depends on variable x and psi, which belongs to 2 copies of R4. Okay. So now I am sorry because somebody entered in the room. So now I am looking for critical points of the following action where you integrate in this space x psi the trace of CV square. So C and V are just real matrix valued function. So you can compute the product, you can compute the square, and you can compute the trace. So here, let me emphasize that V square is not V transposed, and V is not supposed to be symmetric. So, and C is not supposed to be symmetric, sorry. So this is really a square, and there is no obvious convexity in this framework at the moment. Anyway, and now I have a constraint on CNV, which is a kind of quite natural generalization of what we had before for the continuity equation. So let me call that a generalized continuity equation. So in this game now, X more or less substitute for the time in the previous case, in the previous discussion, while psi substitute for the space variable. And you get a balance between the divergence of the first field C with respect to the X variable and the divergence with respect to psi of the second field, which is made of the symmetrized version of CV plus VC. And here I use the standard convention of general relativity, where you sum up implicitly all the indices which are low and lowercase and uppercase. Okay, so there is some additional constraints on this model. So the first one is quite natural and very similar to what we had before, because here I assume that there is some kind of potential for V with respect to the variable psi. So there is just a symmetry condition telling you that actually V has a potential with respect to the psi variable. And there is a more mysterious constraint that we didn't see before, which tells you that in some sense, there is also a kind of potential for C, but you had some diagonal term to be taken into account. But anyway, these linear symmetry constraints are very easy to deal with because they are constant coefficient and they involve only linear constant coefficient operator in psi, and they are much less challenging than the continuity equation. Okay, so this is just a kind of arbitrary generalization, but quite not so unnatural, of the optimal transport problem written in the hydrodynamic style. But now the theorem, it make the connection with the gravity theory, that if you take a smooth solution to the Einstein equation in vacuum, so let me define a smooth solution to be Lorentzian metric G, and the corresponding Levi-Civita connection defined by the Christoffel symbols gamma. So assume that everything is smooth, and now I define my matrix valued field V to be defined on this kind of a phase space where X now is a time space variable of general relativity, and Xi is just the tangent variable in another copy of R4. So X is in R4 and Xi is a tangent vector in R4. And the V is just defined out of the Christoffel symbol by this very simple formula where the Christoffel symbol enjoy 3 indices, and we just let the Christoffel symbol act on the tangent vector Xi, and then we get a field with 2 indices, a field of matrices. And the definition of C is a little bit different. So it's essentially the derivative of some potential vector AJ, while there is a correction involving the Kronecker symbol. And this vector potential A is defined by this mysterious closed formula, which is which I think I found, but it's still slightly mysterious for me. So the definition is entirely given by the metric G, not involving any derivative. And the formula is, as you can see, a kind of a Gaussian type formula with respect to Xi, involving the cosine, but the cosine is just, of course, the real part of the imaginary exponential. So this is like an imaginary Gaussian field in Xi, and the dependence on X is given by the metric itself, and also by the determinant of the metric, and there is a multiplication by the tangent vector Xi. And now I claim that this pair C and V is a solution of the matrix valued optimal transport problem, in the sense that it is a critical point of this, sorry, I'm going the wrong way. It is a critical point of this generalized kinetic energy subject to the generalized continuity equation plus the additional linear constraint. So that's the statement. So this theorem doesn't contain any analysis. It is just pure computation and out of the action principle. So this can be done just by differential calculus. It has nothing to do with any analysis. There is no attempt here to solve the initial value problem for the Einstein equation. It's just a reformulation of the equation, and it's widely open whether or not you could use this formulation for serious purpose in terms of solving the Cauchy problem, for instance. So there is no attempt of this sort in my talk. Okay, so let me just show again Euler upside down, just to show you that the cosine is really the real part of the imaginary exponential, which is a famous contribution of Euler, of course, as mentioned in this stamp from the 50s. And once again, I remind you that in the main statements, the cosine that you can see in the last formula is really just nothing but the real part of the imaginary exponential. And the fact that we are using imaginary exponential is very much related to the fact that we are dealing with Lorentzian metric. And by using a real exponential, we would face very terrible problems. So it's very important to use imaginary exponential. And this is related to the Lorentzian framework. Okay, so now let me comment about the connection between Einstein and Monge. So this is a little bit a repetition of what I already said. So you see that in the Monge problem, we have the space-time in the dimension 1 plus d. And now for the Einstein case, we have the x now substitute for the time, but this is a space-time, it's in R4, and psi is a tangent vector in R4. The matrix is substituted for by the field capital C, the matrix value the capital C, and the continuity equation, the equation de la continuité from the paper by Euler is now replaced by this new continuity equation. And on top of that, of course, the kinetic energy, it's exactly almost unchanged. It's just adjusted to the framework of matrix valued fields. And the funny feature of this new framework that this matrix valued optimal transport formulation of GRV means general relativity in vacuum, looks in some sense much more like continuum mechanics than Lorentzian geometry. So I don't know if there is anything deep about that, but it's quite surprising that you, by just extending the definition of the plane kinetic energy of classical continuum mechanics, you get a good object in the framework of the Einstein equation. So this is a little bit weird, because on the left-hand side, you have something which belongs really to the Galilean mechanics and nothing to do with relativity. However, the formula in the left is very similar, and however, it is consistent with the Einstein equation. Okay, so now let me see that it goes a little bit further than that, because you actually, it is not written in the paper, but as a byproduct, we also found a very strikingly similar optimal formulation of the free Schrodinger equation. Okay, what I'm going to say is not really very surprising, but as far as I know, it has not been written this way so far. So if you look at the free Schrodinger equation, and you could do that also for the nonlinear Schrodinger equation, this would not be a big change. And of course, I am using the very well-known work of Madelung, which was done 1 year after Schrodinger designed the Schrodinger equation, which is, I think, 1925, and Madelung wrote the paper in 1926, and he proposed a hydrodynamical version of the Schrodinger equation just by the simple idea of writing the wave function of Schrodinger equation psi as the square root of some density rho times e to the I theta, where theta was the potential of some velocity field. And you can get a nice set of equations. But you can do that also, which is, I think, not so known, in the framework of complex valued fields. So, which are special, it's a very special type of matrix valued fields, because complex fields can be seen as 2 by 2 matrix valued fields with 2 by 2 matrix with a special structure. So let me use the same notation as for Einstein. So C is a substitute for the density, V for the velocity. So the space-time is the same as in classical optimal transport. And we are looking for the critical points of the integral of the real part of CVK square, sum up from with respect to the dimension index from 1 to D. So this is a space-time integral. And you perform the multiplication of CV square as matrix, but this is the same as the multiplication of complex number. And the trace is just the real part. And we have the continuity equation, which is the usual continuity equation with two big differences. First of all, these fields are complex valued, not real valued. And something which is new in the Schrodinger equation and that you don't see in the Euler, Monge, and neither in the Einstein equation, as I discussed before. So there is an additional dispersive term in the continuity equation involving, of course, the square root of -1, I Laplacian of C. And you can rephrase the free Schrodinger equation this way. So this sounds ridiculous because we know that the linear part of the complex, the continuity equation is already the linear Schrodinger equation. However, if you think in terms of the Madlung transform, which is a kind of a weird way of looking at the Schrodinger equations as a nonlinear equation, therefore this makes sense. And we have a structure which you can see as a third example beyond the optimal transport, the classical optimal transport of Monge, and which is a kind of degenerate version of the Euler equation, and what I just said about the Einstein equation. So at least we have 3 examples of the more or less the same structure. So my guess that this cannot be by chance, that there must be something behind that. Okay, so let me enter a little bit of general relativity. So I think it was not expected in this workshop, but nobody shouldn't worry because because I am not an expert either. And what I'm going to say is absolutely elementary. So the first basic principle in general relativity is you have a Lorentzian metric G, and then when you want to describe the free fall, it just means that you follow geodesic curves in this along this Lorentzian metric if you consider that the topology of the space-time is simple, just R4. And there is several ways of defining geodesics, but you can define that in a quadratic fashion by looking at curves parameterized by S and valued in the space-time R4, which are critical points of the following quadratic action with respect to dx, ds, where you have essentially the square of the S derivative of the point X, of the trajectory X, weighted by the metric evaluated where is the particle. And out of this extremely simple critical action principle, you can get the optimality equation. So this is really a very simple exercise. The first thing to make the exercise easy is to introduce dx over ds as a new field xi, which is like a kind of velocity, but this is velocity with respect to the parameter s. And the optimality equation tells you just that the derivative of this tangent vector psi is just proportional to the square of the vector psi. And the proportionality coefficients are precisely the Christoffel symbol gamma ijk. And you need, of course, 3 indices in order to make this consistent. And it turns out that this Christoffel symbol are just a kind of a logarithmic derivative of the metric. As you can see from this formula, G times gamma is equal to some derivative of G with respect to the space-time variable. So it's extremely simple to get. So there is no mystery out of the Christoffel symbol. They are just what you get in a very elementary way by using the concept of geodesics on this Lorentzian metric space. Okay, so now the basic principle of the Einstein equation in vacuum. So if you are not in vacuum, the equations are more complicated, and maybe I will mention that later on. But the point is that in this very simple situation, the Einstein equation just means that G has 0 Ricci curvature. And it turns out that the Ricci curvature can be defined directly out of the Christoffel symbol. You can define the Ricci curvature, as we are going to see in a moment, directly from the Christoffel symbol rather than from the metric itself. If you consider the Ricci curvature in terms of the metric itself, you get a second order operator. If you consider the Ricci curvature in terms of the Christoffel symbol, we just get a first order operator. Okay, so now in order to give a proof of this formulation theorem of general relativity in vacuum in terms of matrix valued optimal transport, a key idea, at least for me, I mean, I don't know how much this is a standard way to do, doesn't look very standard according to what I read, but the idea is to see the Christoffel symbol as a collection of vector fields on the, actually, there are vector fields on the psi variable which are linear in psi. So the definition, actually, I already said it, but now you can view, you see in the definition of V, you have two indices, J and K. So let's keep the first, the index J to describe the component of a vector field. And K now is more the label of the vector field in this collection of 4 vector fields. So for each, I remind you that K and J are ranging from 0 to 3. So there are 4 possible values, 0 standing from the time, and 1, 2, 3 for the space coordinate, and the time space coordinate is denoted by X. Okay, so let's keep in mind this idea of 4 vector fields labeled by K with component Vj. So now it's a nice trick that I have used. I mean, I have known for several years that it's very nice to encode the Riemann curvature in terms of V, because okay, maybe I am a little bit short. I mean, my memory is not very so good. So it's a little bit hard for me to remind the formula for the Ricci curvature, the Riemann tensor, because of the 4 indices. Of course, there is the abstract definition which not so useful for the computation. And if you want to remember the definition of the Riemann curvature with 4 indices, this is hard for me. However, if you take V, I can get rid of 1 index. And sometimes it is enough to go from 4 to 3 to simplify things. And as a matter of fact, once you do that, you can see that you have a very elementary interpretation of the Riemann curvature as a kind of commutator. So it's known that the Riemann curvature boils down to a commutator, but here this is more straightforward in the sense that you see these 4 vector fields, and you see that the first term is the action of the kind of a Lie derivative of Vj with respect to the vector field Vk minus the opposite. So it's a kind of commutator, very simple one. In this way, I can remind, up to the sign, of course, I can remind very easily the definition of the Riemann curvature. So there is an additional feature, which is typical of general relativity, is the fact that we are dealing with connection with a metric, Lorentzian metric, which are torsion-free, which means that the Christoffel symbol, gamma, j, k, gamma, are symmetric in the indices k and gamma, little gamma. So that's very convenient, because thanks to this symmetry property, the torsion-free property, we can reorganize this Riemann tensor applied to a tangent vector psi in a conservative way. That is to say, we can write that as a kind of divergence in x and psi of a linear terms in the x variable and the quadratic terms in the v variable. which is as simple as this one. And this is this conservation form is related once again to the torsion-free property of the curvature of the metric. And once you have that, of course, Ricci is just a straightforward contraction of Riemann with respect to the only possible in this, I mean, the N and J, sorry, N and J. So you contract N and J. And of course, out of that, you get the Ricci curvature in terms of capital V. And again, you get the same structure, a divergence, which is linear in V, in X, and the quadratic in Psi. And now claiming that the Ricci curvature is 0 just means that you have to solve for V this kind of a generalized matrix valued version of the implicit Burgers equation. And let me emphasize that the Ricci curvature depends directly on the Christoffel symbol, and therefore in this rephrasing, this equation, this 0 Ricci curvature equation, only involves the vector, the matrix valued field V, and there is no matrix valued C in this business. Okay. And now this generalization of the Burgers equation is going to play the same role as the multi-D Burgers equation that we saw before plays for the classical quadratic optimal transport problem in hydrodynamical form. And I will use that in a moment. So before doing that, let me emphasize that at the moment, there is no equation for the metric itself. And therefore, at the moment, I don't know whether I can recover the important property that the Christoffel symbol must derive from G. So which means that the gamma is really the connection of the Levi-Civita connection of some metric. And at the moment, I am just writing a piece of the information. I'm just writing the Ricci curvature of the connection to be 0, but I don't tell you that this connection is deriving from some Lorentzian matrix. So this is the missing part at the moment. So I have not solved the Einstein equation in vacuum so far. I have just asked some connection with Christoffel symbol to solve the 0 Ricci equation. But now we are going to see how the metric itself is emerging from this equation. And for that, I'm going to use the toy model of the multi-D Burgers equation because it's basically the same phenomenon, and it's much easier to explain in the case of the multi-D Burgers equation. So now I'm leaving for a while general relativity, but the strategy I'm going to use is really the same as the one I am using to state this reformulation of the Einstein equation. So let me start from this Burgers equation, which is, by the way, just the gradient of the plane quadratic Hamilton-Jacobi equation. And now the starting point is to write this equation in weak formulation, like in distribution theory, multiplying the equation by a test function, which here is vector valued and denoted by capital A. It's valued in RD because the equation is a vector valued equation. And of course, by integration by part, I get minus dta dot v. Dot is the inner product in RD, minus the divergence of A, written as the gradient dot A, times v squared over 2. That's completely trivial. And there is nothing else. And now this is related to the weak formulation. Let me emphasize that so far, and I should have said that already. So I'm not taking care of boundary condition because I'm just dealing with equations. I'm not dealing with the solution of some initial value problem. So I am totally neglecting a boundary condition. So you can see that. And now the point which is not so much emphasized when you define the weak formulation of some PDEs is that actually it is somewhat fruitful to consider that as a critical principle for the quantity you have obtained through the integration by parts. So let me consider critical points A and V of this functional. And of course, so the functional is still written here. It's the same thing. And of course, when I differentiate with respect to the test function, of course, I just recover the original equation written in weak form. That's obvious. However, if I differentiate in V, I get something, some kind of adjoint equation, if you want, in terms of optimal control. But I get a linear equation in A, of course, because the functional is linear in A, which depends with coefficient depending on V. So I have a set of PDEs, two evolution PDEs, which have a triangular structure. We have a fully nonlinear equation, a nonlinear equation for V, sorry, which doesn't involve A. And you have a linear equation for A slaved by V. So it's a triangular structure. Okay, and now you can play the following game, which is to take your functional again, and you just substitute for the time derivative in the functional the second equation, the second optimality equation. So here it is totally trivial because dTA is equal to minus V times the divergence of A. So in the functional, we multiply by minus V, and therefore we get out of that plus V squared times divergence of A, and minus 1/2 of the same quantity. This is what we get now. We get a new functional that I denote by I sub 2, depending on A and V. But now the critical principle will be of looking at A and V as critical points of I sub 2 subject to the additional equation 2. So it is quite different from what we had before because we start, so let me do the elementary proposition. So whenever A and V is a critical point for the original functional I, then A and V is also a critical point for the new one, I sub 2, but now subject to 2. And I don't know how much time is left. Chairman.
Maybe 5 minutes?
Only 5 minutes. Okay, sorry. So okay, so maybe I can skip that. So this is very elementary. You just introduce a Lagrangian for the new problem because there is a condition. And by some elementary calculation, you see that the proof is just there. So there is nothing. And of course, this is only differential calculus. There is no analysis involved in that. This is just computation. So maybe I can skip that in order to be sharply on time. But actually, if you are quick enough, you can do the demonstration right now. And yeah, so the important trick is that you have to define the Lagrange multiplier in a special way to get the result. And that's the only trick in this calculation. And now, it is quite convenient to write everything not in terms of A, which was the original test function, the vector value test function, but in terms of its divergence that I denote by rho. So, I mean, and then, of course, the equation 2, in terms of rho, boils down to the continuity equation, dt rho plus divergence rho v is 0, because if I take the divergence of the equation, dt of divergence of A is dt rho, and you get the divergence of V time rho. So you get the continuity equation. And in a similar way, of course, I sub 2 is, I mean, this is straightforward, it's just the kinetic energy if you view rho as a density field and V as a velocity field. So you see that out of the simple Burger's equation, which was involving only the field V, I can recover the full optimal transport problem with the structure of involving the kinetic energy, the continuity equation. So as I like to say, if you are an alien living in some extraterrestrial planet, you have never heard about the density fields, the continuum mechanics. You don't know what is continuity equation, but you know what is the Burger's equation. And out of this trick, you can recover the density field, the continuity equation, and the kinetic energy. So you just need to know the Burger's equation, nothing more, in order to do that. Okay, so maybe now you understand my point. So now I'm jumping to the Einstein equation, starting from the zero Ricci curvature equation, which only involves the field V, which is solution to this kind of matrix value, the multi-D Burger's equation set on R8. And out of that, I will recover the equation linking C and V. So this generalized continuity equation, and I will maybe I should, sorry for that, I should recover the formula. Maybe I should have reproduced that again. So I will recover the continuity equation like my alien. So I recover the density, the continuity equation, and I recover the kinetic energy. And now I am ready to prove the theorem. And I have just to perform some a little bit painful calculation to check that with these explicit values taken from a solution of Einstein equation, I satisfy the optimality equation. And by this, I think this was my my final statement. And thank you very much for your attention, and thanks to the organizer for giving me the opportunity to give this talk in the IAS. Okay, thanks. Oh, the sound for me is extremely low.
Yes, I couldn't hear the applause, but there was one.
Okay.
Are there any questions?
Yeah, actually, I have a question. So what if you, like you mentioned that you're only considering Einstein's equation in a vacuum, but if you take that constraint out, would the solution still be optimal transport at the end though?
If I do what, sorry, I missed one.
If you don't view the equations in the vacuum, like if you start adding other things.
If you are the energy tensor.
Yeah, would it still be optimal?
No, actually I didn't do the calculation in that case, but I did it in the quite amazing case, which is, but this is not written up, in the case of the cosmological constants. And in that case, you get something which is almost, looks very much the same as isothermal gas dynamics.
So
the
would
speed
you
of sound
say,
playing the role of the cosmological constant.
So would
and you may
like,
know also there are some there are some very interesting recent results about the so-called Burnett conjecture, that out of the Einstein equation in vacuum, you can get the Einstein equation with matter provided this matter is massless. So this has been recently established rigorously. This was a conjecture by Burnett, and there are some solid mathematical results now. So in some sense, the Einstein equation with matter may be considered as a secondary issue, but of course, in the future, it is very important to do it. But so far, I didn't care so much. You know, this was like.
So is it like a perturbation then to the optimal
Sorry?
transport?
Sorry?
Is it like a perturbation then? Like it's
no,
almost
I mean, this is
like
a very
it, but...
interesting phenomenon of oscillations. So in some sense, depending, of course, it depends on the functional space you are working with. But for the Einstein equation, you can create oscillations and in the initial condition, typically, and out of a limiting process, you can generate non-trivial right-hand side. So in some sense, the Einstein equation in vacuum are not weakly closed. And therefore, there is a natural closure of the Einstein equation by this kind of weak convergent techniques. And you don't get all possible matter terms. So far, I think it seems to be, at least by oscillation, you can generate only mass-free matter. That is, matter that travels with the speed of light.
Thank you, that's a good talk.
Yes. And if you are interested, there is a recent paper by Cécile Hainaut and co-author on these topics. Yes. And this is actually, this is a good way of mentioning the work of Sascha Schnirelmann, because the technique to prove this Burnett conjecture is based on the micro-local defect measure. And you may know this has been invented by Sascha Schnirelmann in the 70s to do the first basic theorem on quantum chaos. So it's very interesting to see the connection with Sascha's work in this framework.
Oh, thanks.
Peter?
Oh, can I ask a question? Hi,
Yes,
Yann.
of course. Nice to see you.
Wonderful stuff. Wonderful stuff. I'm in awe. Wonderful. I, of course, understand very little. So, and relativity, I don't know. But one little thing I know is that burgers shocks. Mm-hmm. And I was wondering, how do these V guys shock?
Okay, that's very nice. Yeah, actually, yeah, I'm completely, I mean, this equation I am writing, so far I am not able to play with them, because one of the main difficulties is the fact that now, instead of the time, we have what substitutes for the time is a space variable, space-time variable. So it's a vector valued evolution equation, and I try to see, it's not so clear, even if there is any theory of evolution equation with several times. So there is, and therefore, I don't even know in which way you can classify this equation. You know, the standard definition of elliptic, hyperbolic, I don't know. And even at the linearized level, it's really unclear to me so far. And there is a baby problem that I didn't mention, which is very useful, which is a complex Hamilton-Jacobi equation. So you take the Hamilton-Jacobi equation with complex valued function. So it is much simpler than this framework. And you may know that this has been studied in the framework of random matrices. So I am referring in particular to work of my colleague from Lyon, Alice Guillonnet, in 20 years ago. And you can see in that case that, for instance, in the complex Hamilton-Jacobi equation, it's more like a space-time elliptic equation. So just by moving from the real value to complex value, you can already get away from hyperbolic. And the complex Hamilton-Jacobi equation actually is a variational equation for which there is a nice trick to get some kind of hidden convexity in the framework. And actually, this is like the equation for optimality equation for a convex minimization principle. So in some sense, these equations are space-time weakly elliptic. So I have no idea, because by moving to the framework of a matrix valued function, by getting no convexity whatsoever so far, maybe there is some hidden convexity, but I didn't see it. And more on top of that, playing with a multi-dimensional variable instead of the time looks like entering a completely different world. So maybe it's a stupid world, a completely useless world, but it seems to be completely unknown, to me at least. And of course, if you have some, especially even on the linear case of PDEs, linear PDEs, well, of course, the concept of ellipticity is perfectly suitable for X and Xi, but the concept of hyperbolicity is really related to, I would say, to the Lorentzian, to the Minkowski metric, where you have the time as a different role than the space, I would say. Well, maybe I should have not mentioned Minkowski because that's nothing to do with this. But I mean, the fact that the time is not treated in a very different way as the space.
All right, thank you. So that obviously I was not hoping to have a general theory. I was just imagining that you played with this on a geodesic or something.
Yeah.
On one dimension. And
yeah, actually, yeah, that's right. So I am a little bit lacking. I was, in some sense, so far I've been a little bit lazy. I mean, this is a quite recent work, actually. This is 6 months old. And I was I am just relaxing after that. And I didn't jump really on the study of the one-dimensional example. Of course, in one-dimensional, you are very likely to collapse to the, of course, you could keep the matrix valued structure and limiting yourself to less variable. Yeah, that's the obvious thing to do, but I have not done that yet.
Okay.
Yeah,
right.
yeah. Thank you. I mean, this is a very good reminder for me that I really should work more on that.
Thank you.
There was another question online. Is that Maria?
Yes. Hi. Thanks. Thanks, Yann, for the talk. I wanted to ask two things. Maybe the first one is how your work relates like to the work of Mondino that you cited and co-authors. And
yeah. Thank you very much, Maya, and very happy to see you. So okay. So far, I don't see any direct connection but maybe I'm lacking imagination because I guess you are more or less familiar with the work of Mondino and Zur. So what they do, they are able to tell you what the meaning of, for instance, Ricci equal to 0 in terms of optimal transport by using this framework of the Boltzmann entropy and the convexity of the Boltzmann entropy along geodesics, which was the basic point of Lott, Villani, and Sturm to say that, for instance, a Riemannian manifold has a non-negative Ricci curvature. This can be written in terms by just saying that the Boltzmann entropy is geodesically convex functional along the geodesic of optimal transport. And a big jump forward was done by Sturm and also, I think, Naber in order to get a characterization of upper bound for the Ricci curvature, which was quite amazing, unexpected. And out of that, they are able to just tell you what's the meaning of to be equal to 0, for instance. And they can also treat matter term. And in this sense, the ideas looks completely unrelated, but maybe there is a link to be done. So I don't know. But it doesn't sound to me, because in some sense, what they do is based on a relatively conventional optimal transport, except that you have to do that in the Lorentzian framework, which was done also by people like Robert McCann, and this is not so obvious. but it is still the somewhat classical optimal transport. And here it's different because this is a reformulation of the Einstein equation in really in a generalized version of optimal transport involving matrix valued fields. So the link is not obvious to me, at least. But
Thanks.
it's very important question, of course, to see whether there is a connection.
Thanks. And the second question is, so there seems to be what you describe a general scheme that you described on the multi-D burgers and that transposes to Einstein. Yes. Is it really a general scheme, for instance, in the other case?
Yeah, for instance, you can do that for the, you can do something similar for the compressible Euler or the Schrodinger equation. This would be, yeah, actually this is a kind of game I like to do, you know, when I have some free time. So I just compute I do the same trick, and this leads to funny computation. Yeah, so it seems to be, but of course there is not really a unified framework. I don't know if it is so important to have a unified framework, but at least we have important examples like a free Schrodinger equation, Euler equations, and the Einstein equation in vacuum. And what is very surprising that these equations are of totally different natures. So, which is very strange to me also, because how can you design an action principle which looks the same, and one is describing classical mechanics, Galilean mechanics, one is describing general relativity, and the other one is describing quantum equation, but which is not relativistic, as we know.
Yes, this is very surprising, but can you say something about the type of PDEs for which these
I didn't try. So the only thing which is I am puzzled with is the Dirac equation, which is the right synthesis between quantum and special relativity mechanics. I don't know how to put the Dirac, just the linear Dirac equation in this framework. And the main reason is that, as far as I know, there is no nice Madelung transform, at least very convincing Madelung. There are some papers mentioning the Madelung transform of the Dirac equation, but this is hard to understand, not so clear to me at least. And I have no idea about dealing with the Dirac equation. And this would be I would be really happy to be able to put the Dirac equation in this framework.
Okay, thank you. So one final question from Steve.
Yeah, hi, Yann. Really nice talk.
Hello, Steve.
How you doing? So I don't know, you probably are aware of this, but back in around 1980, Unruh, the guy famous for Unruh radiation, he wrote a nice paper where he showed that you could take Newtonian non-relativistic irrotational Euler in a flat space-time, and that the sound waves, the fluctuations, are actually governed by a curved Lorentzian space-time metric. So
that could be, yes.
So, and then I think in the maybe around 93, Visser sort of rediscovered this. And I think it might have even been done in the 1920s.
Actually, I remember, actually I had in mind something related to what you say, is this work of Misha Vishik and Friedlander on the incompressible Euler equation, which was a little bit of this nature. You remember this work maybe 20 years ago? But could you give me the name again of this?
Yeah, so there's a paper of Unruh in 1981.
So Unruh, you write
UNRUH.
Yeah. Okay. So
and then a much nicer development is by a guy named Matt Visser, Visser. Visser. I think 93 roughly.
Okay.
And this kind of opened the door for the GR community to study.
Yeah, maybe they actually
using
this
method.
Something.
So if you look at a lot of the GR results, a lot of the results from the GR community, they're actually transforming. They're just studying the D'Alembertian with respect to this particular Lorentz metric. So you can sort of, if you really like GR and you know it well, you can study Euler without actually studying Euler.
Yeah, okay.
Which is really kind of nice for them.
But actually, you remember this work of Friedlander and Bischig, I guess. Yeah, they were because they were using yeah. But thank you very much. Very good.
Okay, I think this was a great final remark. Thank you for all the discussion. Thank you, Yann.
Thank you very much.